There's an option to send file in the chat.
All right, so let's begin. It's my pleasure to welcome Mykola Matviichuk from McGill and the University of Toronto, and he will be talking to us about normal forms for Higgs bundles over a formal 1D disk.
Yes, thanks for the introduction, and I would like to thank you, Peter and Jeremy, for organizing this conference. It's a good opportunity to present the results, and I'm enjoying it so far. So most of what I'm going to talk about, almost everything, is going to be is contained in the appendix to the thesis that I have recently defended in the University of Toronto. So I'll provide a link to the thesis in case you want to look for more details. So let me just jump to what I'm going to talk about. So I start with a smooth curve over complex numbers and a holomorphic vector bundle over a curve. And a tensor of this type is called a Higgs field. So it's a matrix, essentially everywhere locally it's a matrix whose entries are 1 points in the curve. And so that's very well known, very well studied notion introduced by Hitchin. And the bundle with such a Higgs field is usually called Higgs bundle. So also I like to consider dual notion, which I call co-Higgs field. That's where when you twist, instead of twisting by a cotangent bundle of the curve, you twist by the tangent bundle. And then the bundle with such a tensor is called co-Higgs bundle. So this terminology co-Higgs is a little ambiguous, so some authors quite reasonably call this still Higgs field, no matter what twisting you choose. And I think if you look in the thesis of Stephen Ryan, who wrote the thesis on geometry of co-Higgs bundles, he still would call this tensor Higgs field rather than co-Higgs field. But so there is a little bit of ambiguity in terminology. But when the curve is affine, or in this particular case, which I will be considering when the curve is just subset of C, then it doesn't matter which twisting you choose because it all end up being the same. So the two notions will coincide in that case. So let me briefly recall spectral correspondence for Higgs fields. So that's for that you really doesn't matter which twisting you choose. You can twist by any line bundle. So if you twist by a line bundle L, then you can consider such a tensor as a matrix whose everywhere locally it's endomorphism. It's essentially a matrix whose entries are sections of L. And so you can consider a determinant of such a characteristic polynomial of such a matrix, and that will be a section of some symmetric power of L. And you can consider a zero set of this section, and that's called spectral curve of the Higgs field. So it's called spectral because intersection with each fiber encodes the spectrum of the matrix. It's called the eigenvalues of the matrix. And moreover, when you have a spectral curve, you can also construct a sheaf over it that encode the eigenvectors of the matrix. And so Bovil, Narasimhan, and Ramanan, they phrased this correspondence. They phrased this nice correspondence between vector bundles and Higgs fields on them, and the pairs of a curve and rank 1 torsion-free sheaf over the curve. So to go here to the right, from left to right, as I said, you just take a sigma encodes eigenvalues, and the sheaf encodes eigenvectors. And to go in the opposite direction, you basically push forward the sheaf that will give you the vector bundle. And if you push forward the action of the multiplication by the tautological section of the pullback of L2 itself, then it allows you to recover the Higgs field. So this is a very nice picture that kind of allows you to introduce some geometry into studying of this Higgs field. That's very well known. So the question I'm going to consider today is what happens if you fix a curve. Right. So suppose we are working over a formal disk rather than global curve. So you can think of also just small analytic disk. And suppose you have a vector bundle of fixed rank, which necessarily has to be trivial. And suppose you fix the spectral curve of the Higgs field. And the question is, what can be said about the Higgs field? Is there maybe normal form for such Higgs field? Or maybe there are a couple of normal forms allowed, like possible for such Higgs field. And this question has a very nice answer when the curve is smooth. So for instance, and it's like this R21 branched cover of the base. Then it's very well known that all Higgs fields are isomorphic to each other, and in particular you can choose a basis so that the Higgs field would rotate the basis, and then it would multiply the last one by x and send to the first position. So it would have this nice matrix. So that's a local normal form for such Higgs field when the curve is smooth. And the question I want to know is what happens when the curve is no longer smooth? Is there some type of nice results of this sort? And so I encountered this question while doing my thesis, and I started searching literature, and I found very few cases written. Basically, the only case I was able to find in literature was when you had like simple normal crossing singularity for the curve. So I had to work out some of the cases myself, and so I decided to present it today. So maybe some of you would recognize that it's already, somewhere in the literature, so that I can give proper credit. So before explaining this, before explaining my results, let me first explain why I needed to consider this problem in the first place. I mean, it definitely looks like a very natural question to ask, but still I had very particular application in mind for this. So let me make a little detour and explain why one would want to consider, why I wanted to consider this question. The motivation for me came from Poisson geometry. So I was considering vector bundles over a curve, and I was considering a Poisson structure on vector bundle that is invariant under the dilation, star invariant. And it turns out that such Poisson structure automatically gives you a co-Higgs field on the vector bundle. And the procedure is the following. It's quite simple. So you consider the co-Higgs field as a sheaf map from a T star, from cotangent bundle to the sheaf of endomorphisms of V. And so how you construct this sheaf map, you take one form on the base, you pull it to the total space of the vector bundle, and you take Hamiltonian vector field of that pulled back form, and you check that it's a C-star invariant vector field tangent to the fibers. So because it's a C-star invariant vector field tangent to the fibers, you can canonically interpret it as an endomorphism, a section of endomorphism bundle. So that gives you a co-Higgs field. And analogously, and quite similarly to this, if you just start with Poisson structure on projectivization of the vector bundle, then you can also obtain a co-Higgs field on this vector bundle. So I will study an interplay between co-Higgs fields and Poisson structures on vector bundles or projective bundles. And I can micro this fact that if you consider rank greater than 2 over a curve that is simply connected, then whenever you have a Poisson structure, either on projectivization of the vector bundle or cistar invariant Poisson structure on the vector bundle itself, then it turns out that the spectral curve of the corresponding Higgs field, if it is connected, it must be singular. So just connectedness is just condition to avoid just spectral curve having a couple separate branches that don't talk to each other. It's kind of like simple, boring case. So to avoid that, I just impose that the curve is connected, and then it necessarily has to have singularities. So even though you start with a Poisson structure that is perfectly smooth and nice, but at the end you have to deal with the singular objects, which are spectral curves of the underlying Higgs field. So that somehow motivated me to look at that. Okay, so let's come back to the problem. So I start with the formal disk. I have a vector bundle fixed rank, and then I suppose I fix a singular spectral curve. And I'm asking question, what can I say about Higgs field itself? Okay. So by spectral correspondence, the question, the isomorphism classes of the Higgs fields with fixed spectral curve and one-to-one correspondence with torsion-free rank 1 sheaves on that curve. And so here I have to thank my my old friend Vladimir Gavran. I asked him this question, and he knew where to look. So he pointed me to this old literature where these sheets described. And it turns out that for special singularities, such as AD singularities, something called TPQ singularities, and a couple more, this problem is actually was solved a long time ago in algebraic context. So just to remind, let me say what are these singularities, AD and TPQ. So AD singularities are given by these formulas. You can associate linking diagrams to them. And TPQ singularities, they typically have like one parameter in the definition. That's why they call it unimodular singularities. And for my thesis, I needed just a couple of them. I didn't need everything. I just needed essentially these 5 cases, which I draw here. So these are the singularities that I'm going to discuss today and present some results about Higgs fields with this type of singularities for the spectral curve. Okay. So let's jump to it. So let me start with AN singularities. That's perhaps maybe, I strongly suspect it's a well-known case, but let me just say it anyway. So this AN singularity is given by this equation. You can choose, you can change coordinates to bring it to this form. And suppose you start with a Higgs field with this spectral curve, then turns out that a Higgs field is isomorphic to one of the finite, there is finite list of local normal forms for such thing. So it's either isomorphic to this matrix, where you permute the bases, but the last one you multiply by x squared before you permute it. And that corresponds in spectral correspondence that means that you start with a just trivial sheaf on the spectral curve. So that's one possibility, and then there is another family of possibilities when you take the AN singularity and you do a couple blow-ups, you create partial resolution of singularities on that curve, and you take structure sheaf on that resolved curve, and push it forward on the original curve. So that would, each time it would give you different torsion-free rank 1 sheaf, and that would correspond to different Higgs fields. So there are finitely many ways to do it, and it's something like somehow the answer would definitely, if you kind of like thought about it for a while, probably what you would have come up with, but in fact, these are the all possibilities you can have here. So there are roughly n/2 isomorphism classes for the Higgs field with this spectral curve. Okay, so the next case, I have written results for any dn singularity, but let me discuss d4 singularity because it's already quite interesting, and it's the one I actually need. So it's the singularity when you have three lines meeting at a point transversely to each other. So for that case, so let's fix a Higgs field with such spectral curve. And it turns out that you have the following options, the following isomorphism classes for the Higgs field. Okay, so I'm going to draw now pictures to denote this matrices. So the formula for matrices are not very particularly illuminating, but I'm going to include the pictures, which would be pictures of the partial desingularizations of this singularity. So on the first option, when I don't desingularize anything, I just take the structure sheaf of the curve itself. So I drew here a d4 curve itself on the left, and that gives me this first matrix. Then I have the following three options. I can take one of the curves apart, or one of the lines apart from two others. There are three ways to do it, and by pushing forward a structure sheaf of such a curve onto sigma, I can get three different torsion-free rank 1 sheaves, and that would give me three different Higgs fields by spectral correspondence. And then the final option, when I just completely desingularize my curve and take just all three branches apart from each other. So these are quite expected options, but turns out that there are two maybe less expected isomorphism classes. So this happens when you just take one of the lines and move it away from the plane containing the other two. And it turns out that it doesn't matter which one you move. So this desingularization is unique. But what's happening here, that because the singularity is no longer planar, it happens to be non-Gorenstein. So so that means that the dualizing sheaf of this curve is not isomorphic locally to the structure sheaf. So you can either take structure sheaf and push it down on the sigma, or you can take the dualizing sheaf of this curve and push it forward to sigma. And that would give you two different isomorphism classes for the Higgs field. So those are all the options. So you have seven isomorphism classes for the d4 singularity. In this case. Okay. Any questions about this? So the theorem says that whenever you start with any Higgs field with this spectral curve sigma, then you can conjugate it to one of the seven options. Okay, and let me present maybe one more case. That's E7 singularity. So that's given by this curve. You saw a picture already, but I'll draw it again on this slide. So if you have a spectral curve with E7 singularity and you have a Higgs field with the spectral curve, then you have the following options. So first option, when you just take structure sheaf, apply spectral correspondence and obtain this Higgs field. Then you can do just take the two branches apart and not desingularize this cuspidal curve. Then you can also desingularize the cusp and but leave them connected, leave them intersect each other, or you can do both. You can also take them apart and desingularize the singular branch. So those are 4 obvious options, but now there are a couple more not so obvious. So this one is similar to what we saw before for D4. It's when you take the line and move it away from the plane containing the cuspidal curve. So again, so it gives you can take either structure sheaf or dualizing sheaf of this curve and push it forward onto sigma, and that will give you 2 isomorphism classes. And then finally, you have also this option when you move the straight line away from the plane, but make it tangent to the plane containing the cuspidal curve. And it turns out that there's yet another different partial resolution possible in this case. And by taking structure sheaf or dualizing sheaf for this curve, you obtain 2 different isomorphism classes for the Higgs field. So in this case, we have 8 options, 8 isomorphism classes for the Higgs field with this singularity. Okay, so so let me just say that I consider more cases in the appendix to the PhD thesis that I wrote under supervision of Marco Gualtieri. So you can find the copy of the thesis online. And I would I would really appreciate if someone would just point out to me that if these results are already somewhere written so that I can give proper credit. And I must say, just maybe because we have a couple of minutes left, I want to advertise what I do in physics using these results. So I just take these local normal forms and I study which of them produce some Poisson structures for me on vector bundles or projective bundles over curve. So I start with considering them over disk, over unit disk, as I did in this topic, in this presentation. So I start with all these isomorphism classes that I was describing, and I find out which of them can be lifted, so to speak, to a Poisson structure on projective bundle, Poisson structure on the vector bundle. And then after that, I proceed to globalizing this picture and consider what Higgs fields over P1 give rise to certain Poisson structures on Pn bundles over P1. And I discussed in detail the case of P2 bundles over P1. And using this technique, I can actually obtain classification of Poisson structures on P2 bundles over P1 under additional technical assumption that the spectral curve of the underlying Higgs field is reduced. Okay, so I think maybe that's all I wanted to say. Let me stop. Thank you.